Okay, so let's get started. We're finishing up mid-level vision. So we have this just one more lecture before the midterm. So make sure that you review all the handouts that you have in Canvas and the homework that you have been working on. And obviously the recitation sessions where we covered a lot of the details of some of these algorithms, right? Okay. Any questions before we get started on the previous lectures? Nope. All right. So today we're gonna do just one lecture on segmentation, and we'll discuss a variety of methods. I'll just summarize the main ideas behind the methods because they're all very similar. In fact, they just use slightly different tools, but tools that you're already familiar with. So shouldn't be difficult at all, okay? All right, so let's get to it. First one, I'm gonna talk about image segmentation, or some of the ideas. Let me start with this. I'm going to start talking about some of the ideas back to the Gestalt psychology. And psychologists, many years ago, decades ago, when they were considering how the human visual system organizes things. Remember in that classical model of the visual system where we assume in the ventral visual path that there is low-level vision and mid-level vision. So low-level vision, we've already seen quite a bit of this on how to detect image features that can then be used by mid-level vision to organize these features in some way that is useful for then higher level tasks like object recognition, which are going to be most of our second part of the course, obviously. So Gestalt psychologists started considering a variety of things that could be done, and they realized that there is a number of properties that people use to organize things from an image. So for example, one of them, number one, would be proximity. And proximity means that if you have, say, 2 points like this, they're very close to each other, and 2 other points like this, they're very close to each other, but these 2 are far from these first 2, right? People tend to classify this as one group and this as another group, right? So distance between the elements, between the features, between these low-level features that we're extracting from the image actually matter, okay? Number 2 would be similarity. So similarity means that if I have a point here and at a distance I have a point that's exactly like this, and then at the same distance from this, so if this is this distance, at the exactly same distance, I have another point that is in another color or another texture or another shape, and then I have another one here, then people tend to classify these two as one group and these 2 as another group, right? And that's because they are similar. They are more similar to each other. Okay. There's another one which is motion similarity. Sometimes you will see it as common fate. And what that means is that if you see, I cannot draw this here because I need motion, but you have probably seen this. If not, Google it, right? Or go to YouTube and search for this. And, you have these videos of a certain number of points that move in unison And then when they move in unison, if you have points moving in one direction or in one three-dimensional rotation, for example, and another set of points moving another or according to another three-dimensional rotation, then you see these two different groups, right? Even though they're just dots in a screen. You've all seen this, right? So that's what is meant by this, that we also cluster things according to this common fate. Number 4 would be parallelism. And that means that if I have, say, an object like this, and then an object like this, right? Even though they're equally close, these functions, these curves, these two are clustered together and these two are clustered together, right? Because they are, one parallels the other. Number 5 would be things are closure. Number 6 could be symmetry. So for example, if I had something like this and then something like that, right? There is a symmetry in here, right? It's symmetric, it's a mirror image. So these tend to be clustered together, and these two would be clustered together as well, right? So symmetry also matters. 7 would be continuity. And continuity means that if I have, for example, an object like this, an opaque object, right? And now I have two objects behind it. Say that one goes like this, and maybe you have another one that goes like this. Actually, let me do it like this, right? We assume we cluster these two together and these two together because there is a continuity here, and we assume that there is a continuity of this curve, right, behind that occluder that connects these two elements, right? And most of the early work, if not all the work that has that we have had in computer vision with regard to segmentation is based on these concepts. The only other one that is not based, or the major one that is not based in Gestalt, it's the one that's based on object categories, right? Like a car, a table, a chair, and so on. And we'll get to that much later on in the course. But the ones that we're going to discuss today are mostly based on this, on these concepts. Okay? Any questions? All right. So let's see how we can design algorithms to do segmentation. The first algorithm I want to talk about is the simplest, and it's called background subtraction. Okay, so in many images, I'm going to have a background that is, or in many images, in many applications rather, I'm going to have a background that is constant, right? So maybe I have a camera looking at this room, the entire room, right? Wall to wall. And that room barely changes, right? I mean, you can move the chairs around, you can move the tables maybe once in a while, but rarely changes. What changes is what's in the foreground. These are the people coming in and out in that case, right? And I want to design an algorithm that detects the foreground and subtracts the background from my images, right? So how can I do that? Well, let's think about the simplest algorithm of them all, right? The simplest algorithm is that they can define a variable, let's say b for background, that at iteration n plus 1 I define it as Fn. That would be the frame or the image, the nth image, right, at time n. So my image at time n. Plus the sum of my backgrounds at different times prior to n. So let's say n minus I from 1 through n minus 1, right? Okay. Or if you want in general, you can just say from 1 to k, because obviously k has to be smaller or equal than n minus 1, because I'm only considering the previous k frames, right? I don't have to consider all the previous frames. And now I'm going to add some constants here, some variables, some regularizers, if you will, that determine the relevance of each of these two terms. And usually you normalize this by some other term, okay? So that algorithm, I have to say, doesn't work really well, but for very simple applications, like if you have to build a computer vision system in a factory where, I don't know, maybe boxes are moving by, right? And you have to determine which ones go to this zip code versus this other zip code, and you have to have robots moving them around. Well, that background is probably so constant over time that this algorithm will work just fine, right? Illumination never changes. The camera, if it moves almost imperceptibly by just 1 or 2 pixels, and so on, right? So in that case, all you need to do is over time, so starting with a picture of the background. So you take a picture of the background and you set it to B0, right? That's your initial background. And then as things happen, you keep adding a portion of the current image, right, that has both the background and the foreground. But because over time you're summing over many, many images, the pixels that correspond to the foreground basically dissipate, right? They disappear. Not completely, but mostly, right? That works especially well, as I said, if the amount of pixels in the foreground are very small and they don't occur very often, right? All right, you see how this works? Very simple. Now, obviously, there are better ways to doing that. One way is to identify that background image, right, from a set of observations, right? So think about this. I take, say, images of my scene, say this room, over a 24-hour period, right? Now, I can define each of these images of p pixels in an RP dimensional space, right? We've seen how to do that. You take the pixels of the image, and each pixel corresponds to one of the entries of a p-dimensional vector, right? And now you have a feature vector in that RP dimensional space, right, for each of the images. Now, do we know of a method that will extract the common elements of those feature vectors in RP? What's that? PCA. Very good, right? Linear least squares, basic linear least squares. So here's how it goes again. So I have a set of n images, let's say, okay? And I vectorize them, meaning that I have, for the first image, I have a vector x1. For the nth image, I have a vector xn with all the xi's in RP, right, in p dimensions. And that means that for each image, I get a vector, right, some vector representation here in my RP dimensional space. And then what is most common in all these images? The background, right? So you can actually take your least square solution, the hyperplane that best approximates all these different points, and that's going to define a model, right? A least squares model of that background. And that model is given by PCA. Very good. All right. Now, let's see. So, okay, maybe we'll do that. So here, this is number 1. Number 2 would be the PCA solution, which could be given by, so first xi is equal to a vector form of my fi's, right? The fi images that I had over here. And then b, I will compute the covariance matrix, sigma x, right? Remember, covariance matrix. And c, compute the first, compute or obtain the first k eigenvectors of sigma x. Now, what I mean by the first, remember, I always order them from largest eigenvalue to smallest eigenvalue. So the first are the ones that are associated to the largest eigenvalues, right? And then d, so let's call these eigenvectors, I don't know, AK, right? A matrix AK whose columns are the eigenvectors, okay? And then define B, right, the background, as a subspace of AK with AK transpose, right, XI, right? Yes? Okay, so for each XI, I project that XI to the subspace defined by that background model, and then I project it back onto the image, right, onto the size of the image. And what do I recover? I recover the background, right? Okay. Now, this method is really good, or at least let me say this. This method is a really good idea, but it's not going to work, or it's not going to work really well. Why? Yes?
Because actually, it's also a question. So I feel you use PCA, right? You can't guarantee the feature you extracted from PCA is absolutely the background.
Why not?
I mean, why can't we determine that?
Because that's, if the background is constant, right, throughout all the images, then remember, each of these dimensions here represents one of the pixels. So that is going to give you the most common value of that pixel throughout this thousands, hundreds of thousands, or even millions of images. And what is that common pixel? That's a background. Because in some images, you're not going to have that pixel to be the background. And most of them will be a background pixel, right? But in some of them will be a foreground, but only in some of them, right? Because the foreground changes over time, but the background stays pretty much the same.
So we assume the background is constant,
right? Right, right. So that's why this method doesn't work in practice, because the background is not totally constant, right? There could be illumination changes. I could move that chair. I could move a couple tables around, right? So do we know of a method that can address that problem? So if that happens, what happens in my data set? What do I have in that set of x1 to xn, my symbols? So I still want to use something very similar, but I want to solve a very specific problem. What is it?
Sparse coding?
We haven't seen that. That could be a way to address some of the issues, but not the issue I'm referring to. Right. It's something that we have covered here in this course. Why? Why would that be a good idea? I don't know why that would be a good idea. Maybe I'm missing something, but no. If the background changes, let's say, right, that they move a couple tables there, then what's going to happen? Some of the images are going to be very different from all the other images, right? And what we call these images? Right. Very good. Robust PCA. How do we call these images that are different? Outliers, right? So we're going to get rid of them. And we already know of a method that can do that. Very good. That's robust PCA. So typically you will do that too, but unless the background is so constant that nothing moves, the illumination is super constant, et cetera, or you're going to use robust PCA to be robust to all these image changes that are inevitably going to occur. Okay? All right. So the next topic, or the next set of methods that I want to talk about is a graph-theoretical clustering, segmentation by graph-theoretical clustering. Now, we've already covered graphs, right? When we talk about deep neural networks, remember? So you already know what a graph is, but we're going to use the exact same idea of graph, but now the nodes are going to represent either pixels or some property of some features of low-level images, of the low-level features that we extracted from the images, okay? So, let me start by assuming that we have a connected, well, actually, it doesn't matter. Well, it's a directed or undirected, a weighted graph. That's what matters. Okay. Either directed or undirected. Now remember that we can represent such a graph using a weight matrix. Let's call it W, okay? Remember the weight matrix that has the number of edges by the number of edges, right? And at each entry, the number of nodes and the number of nodes, rather. And each entry corresponds to the weight of the edge between these two nodes, right? Okay, great. Now, obviously, if it's an undirected graph, then that matrix is symmetric, right? Because the weight from I to j is the same than the weight from j to I, right? Okay. All right. So the key idea here, is that if we do clustering means that we group different elements of something, right? If we do clustering in this matrix, that's called the affinity matrix, if you recall that. So this is called the affinity matrix. If we do clustering in the affinity matrix, that's equivalent, or that's the same as doing clustering or if you prefer, cutting the graph into subgraphs. Okay? So dividing or cutting the graph into subgraphs. Okay? So somehow that graph has to represent the pixels in the image, right? And obviously the simplest way is each node of the graph represents a pixel in the image. It could represent what is called a superpixel, which means that it's a number of pixels, right? A local region of the pixels of the image, and so on. Okay? All right. Once I have this, if I describe that graph with its affinity matrix, then doing clustering in that affinity matrix is the same that subdividing this graph into subgraphs. Okay? That's a basic concept. So the first thing that we need to define is how we're going to compute that affinity matrix. Okay? So let's see that. Okay, I'm going to call these affinity measures. Okay. Okay, so I would need to define a measure, an affinity matrix, right, that specifically defines or has similar values in its entries for pixels that should be clustered together, right? That's what I want. Okay. So as we did with Gestalt, one of the first ways to compute that is to define an affinity distance, right? Or the affinity measure be based on distance. Based on distance. Okay. Now, so for example, I could do, if I have pixel x and y, I could do x minus y. Now, this can be positive or negative, so I can just do the Euclidean distance, right? Or the square of the Euclidean distance would be this one, right? Correct? Okay. And that would be fine, but it would be better if, for clustering, if things are very close to each other, are very well marked and compared to things that are really far away, right? So for example, things that are really far away, I want them to dissipate really quickly, right? Let's say exponentially, right? Even better, right? Rather than linearly, I want them to go exponentially. So what function could I use? Any exponential, right? So the exponential function of this. And because this is an exponential function, let's normalize it by some variance. And that variance is going to determine how far out I need to go before that exponential curve falls out, right? And so 2 times the variance squared, for example, right? And maybe I can call this sigma d to identify this is the variance according to that distance that I measure, right? Now, obviously, you could change that, right? So this could be an option A. There could be another option B that is based on some other distance, right? So I could have here thus then M inverse x, y, where M is any symmetric positive semi-definite matrix that specifies a metric in a Hilbert space, right? If you remember Hilbert spaces from 5460, that's what we covered, right? That you can define all these metrics, all these different metrics, and that's how you measure the distance, right? And the distance is given by that. Now, if that matrix is the identity matrix, then this is the Euclidean distance, or the square of the Euclidean distance, right? And you can interpret this because, or the way it's typically interpreted, is that if you have 2 dimensions, then the identity matrix is 1, 1 in the diagonal. So the identity matrix should be something like this, right? 0 in the off diagonals, 1 in the diagonal, right? And what that means is that for along this distance, the weight that I give to that measurement is 1. And about this distance, or about this axis, rather, the weight that I give to that distance is also 1. And therefore, that gives me the circle, right, of the 2 norm. The 2 norm, or the corresponding Euclidean distance, right? And then as I change that M, right, I can make that metric look maybe like this, or like any other ellipsoid, right? And by deforming that ellipsoid, what I'm saying is that this distance is going to be, or this distance, this axis is going to have more relevance than this one, right? It's going to be shorter, right? There's the weights in the diagonal are going to specify the shape of that metric, right? So obviously, you can change that very easily depending on your needs for segmentation. Another thing that you could do is you could compute similarity based on pixel intensity. Okay, so in that case, maybe we should say, let's do this. Maybe we should say this is equal to WXY, right? This is the W, the weight of the affinity matrix that connects pixel X and Y, right? And here, my weight should be equal to, again, the exponential of, now what I'm going to do, I'm going to do the same I did before. But in this case, I'm going to use I of x, right? Where I of x is the intensity at pixel x, okay? And as always, I normalize this by some sigma. I'm going to call this sigma I to differentiate it from sigma d. You may want to be using different sigmas, right, that determine how that exponential curve falls down depending on the type of measurement that you use, right? We could do other things. Let's see. We could be basing this on some linear filters, for example, right? So we could compute, let's see, Gabors. We could compute edges. We could compute some other types of wavelets. We could compute deep features, right? We could extract any property of the image that we want, right, with a functional mapping H. So remember that when I apply a linear filter, like a Gabor, that's nothing else than applying a linear mapping, right? H of x, right? Or a nonlinear mapping, H of x. And when I do, when I compute the PCA basis vectors to create that space, I do another type of mapping, right? The PCA mapping. And when I use the features, I use another type of mapping, right? So all these mappings can be defined as different measurements of filters. So let's just say low-level image features given by some function h. Okay? And then with that, I can define my weight as the exponential function of h of x minus h of y transpose, this is transpose, times m inverse hx minus hy divided by 2 times some sigma. Okay, maybe sigma h this time. Okay, you see how this works? And so on and so forth, right? So you could go on like this, right? Defining measurements based on whatever property that you think appropriate. Now going back to Gestalt, you can think about defining measurements based on parallelism, right? Have we seen a method maybe that we could use to determine whether things are parallel or not? Maybe some tools from projective geometry, right? Yeah. So you could use that. Could you use to see if they are mirror images of one another? Yeah, projective geometry again, right? Could you see if there are things that are identical up to a similarity transformation, or an affine transformation, or a projectivity, right? And so on, right? So all these things we can now use to define any number of measurements that we want to give, or to compute to define our affinity matrix. Now, that is just the first step, because that is what we need to compute or to have an affinity matrix W. But now that I have W, I still need to cluster that W. How do I do that? Let's see that next. All right. So now that I have this, I want to know, I need to define some criterion to cluster my different elements of W. Okay? And I'm going to give you 2 methods. There are many methods in graph-theoretic clustering, but I'm going to give an overview of 2 of them. The first one is called the CAT algorithm. CAT algorithm. And that's very simple. In fact, what it does is it says, let's suppose that I subdivide my graph. So my graph G subdivided okay. Subdivided into A and B, and we want A intersection B to be null, meaning there's no overlap between A and B, right? So a node is either in A or in B, but it cannot be in both. And A union B should be equal to my whole graph, right? Okay. And maybe let's say not the graph, but let's say if that graph is equal to some V and the vertices and the edges, right? That this should be equal to the vertices, right? The nodes, all the nodes, okay? And now our criterion can be simply given by the sum of the weights between, actually let's do it this way as we did before, wij, right? The sum of the weights for every ai, for every I in A and every j in B, right? So if I compute the weights, the sum of all the weights that go from every element in A, right, subset A, to every element in B, what am I measuring? I'm measuring how strong the connection is between these two separate clusters, right? So do I want to maximize this or to minimize this? Minimize, right? Because I want to separate the groups that are more similar to each other. And therefore, the similarity between these two groups has to be minimum, right? OK. So I want to minimize. I want to find the AB sets that minimize this equation. All right. Now, I'm going to post a paper in Canvas that shows how to do that, what's the best way to do this. But anyone has an idea. The intuitive idea is trivial, but the derivations are not too long, but we don't have any need to keep repeating the same derivation. But anyone can tell me how you think you could find that these two subsets A and B that cut in the graph. So the cut you have to, or the clustering, you have to do it in the affinity matrix, right? So what method do we know that's going to give us two subsets that minimize some criterion? You always think I ask tricky questions, and I don't. Really? You don't know of a method that can do that? How about over there? Anyone? Well, sure. But what's a generic name for that method? Anyone? How about least squares? Seriously? Right? So yeah, it is. You can solve this with linear least squares. So you have the derivations. And in fact, the eigenvector associated to the smallest eigenvalue, right? Of d minus w e lambda e, right? E the eigenvector, lambda the eigenvalue, where capital D here, it's the sum of my wij's for j1 through n, okay? And this would be my entry, ijth entry here. Okay, so D is just a normalization term for W. So yeah, you just do clustering using PCA, right? Same thing, eigenvalue decomposition rather, which is least squares. Okay. Again, I'll post the paper in Carmen. Please look into this. So this is the cut algorithm. The second one, it's an extension of that algorithm, which is called n-cut. And the problem with the cut algorithm is that if I have something like this in my space defined by the affinity matrix, let's say that I have something like this, right? Maybe I'll do this. the cut algorithm will always give you whichever cut minimizes that equation over there, right? Which will probably be over here. But you may be interested in something that is more even in number of pixels between the different cuts, right? Because it's very rare that you're going to have such a small, tiny cluster here and then all this huge other area corresponding to a separate cluster. It could happen, but it's rare. And if that doesn't happen, then this normalized version of the cut, which is defined as the cut between A and B, that's the criterion that we have defined here, okay? Divided by a term that normalizes this. This is called the association between A and V, to be defined in a second, plus the cut between A and B, and the same between B and V, okay? Where that new function, this normalizing function, measures how big that new subgraph is. And how can I do that? By taking all the elements of A and connecting them to all the elements of all the nodes of the graph, right? So this would be for every I in A and every J in V, right? Make sense? So that way you normalize by the size of the subgraph, so you're guaranteed that the sizes of the subgraph are closer to each other, right? Or unless there's not a huge divergence between their sizes, unless the difference of the metrics that we have used here, or the measurements rather that we've used here, are extremely large, right? And you can get the solution with the eigenvalue decomposition that we have defined here. And now you need to use the generalized eigenvalue decomposition. It turns out, in fact, that you can do something even better. Because with the n-cut algorithm, if you just take the eigenvector associated to the smallest eigenvalue of what's called the Laplacian matrix, right? Then you only get 2 clusters in the image. But an image might have a number of clusters, right? A number of regions in that image are clustered together, not just 2. So how would you solve this? Well, first way to solve this, very straightforward. You divide the image into 2 chunks, right? And then you take each of these 2 parts, and you divide each one with the same algorithm again into 2 components, right? So now you have 4. And you keep repeating iteratively within each new component, until in each of these components that the similarity measurements that we have compute in that subgraph are very, very high, or over a threshold, right? And then at that point you stop. So that's one approach to do that. But with the n-cut, because you get more eigenvectors, what you could do is you could take all the eigenvectors associated to non-zero eigenvalues, because for the n-cut, the last eigenvector is associated to a 0 eigenvalue, and that's meaningless. It hasn't, I mean, it's not meaningless, but it's not, doesn't have a use for us in cutting the graph. So you take all the other ones, and now you define the affinity matrix in that eigenvector space, okay? And once you have defined that, you can apply machine learning algorithms to do clustering in that eigenvector space, okay? So those are all the different options that people work with when they use these methods for clustering. And there are many other types of cuts criteria that have been defined, okay? Just want you to know. So they're not the only 2 that you're gonna see in the literature. Okay, so another set of methods that I want to go over are based on, I'm going to go through this really quickly, but it's important to mention at least. There is a set of tools called Markov random fields that can also be used and have been used very efficiently to cluster, to do image clustering especially, especially medical imaging. Okay, so Markov random fields. And the idea is that we can, by modeling what's called local effects in the image, we may be able to define global properties of the image. And Markov random fields use two concepts that I have repeated here in this course, but especially in machine learning class all the time, and to a lesser degree maybe in 5460 as well, which are, first, that you have your data, X. This is your observation, what you can observe in the world, the image that we have in our case, right? And in fact, you could say I have a set of them, X1 through Xn, okay? So these are my observations. And then there are Z, oh, actually, let me do, just my notes are the other way around. So these are, Z rather, are my observations, Z, N. So these are my observations. And the X's are the actual data I'm interested in, right? Okay. So another way to say this that we've used here before is to say these are the sources, right? And then you just build a linear model. So the first step for a Markov random field is to define some type of model. The simplest model that you can use, it's a linear model like this. Z, your observation, is equal to X, right, multiplied by some transformation matrix H plus some noise term N, right? Okay. Now, typically, N in Markov random field, it's modeled as a Gaussian or as a Gaussianly distributed noise. So it's a random variable that is drawn from a Gaussian distribution, right? So this will be drawn, N is drawn from a normal distribution with some mu and sigma. And typically, what most people will assume is that this Gaussian is zero mean and identity matrix for the noise term, okay? Typically, but you will see other variations, okay? You can also have a prior probability for your data X, capital PX, right? There would be the prior probability on X. Or maybe you have a known distribution for P of X, right? Which again, maybe could be modeled with a normal distribution with some mean and variance. So one way to define this formally here would be, let's say, I could define my distribution as an exponential function, right? Meaning a Gaussian type of function, negative v, where v is equal to X transpose MX, right? For some matrix M. And that, what this is nothing else than a quadratic equation, right? That's all I'm doing. I'm just defining it as a quadratic equation because it's easy to work with. Then if I do that, I could compute the probability of my observation given X, right? And that would be, say that I define this also as proportional to the exponential of negative u, where now, if I compute this, u is going to be z, right? We do have z minus hx. Okay, perfect. And I'm going to square that. And maybe I want to normalize this by the variance or by some noise term, right? Okay. And then the criterion, or what you want to, the criterion that you want to maximize, obviously, the goal is to maximize the probability of x given z, right? So I want to find the x that maximizes the probability, the conditional probability of x given my observation, right? And at any rate, you will see Markov random fields that people model this, right? And the question is, how are you going to model the probability, the pi probabilities? How are you going to model this? Like, for example, as I've shown you here, but there are many variants, right? And then using the Bayes theorem, you can compute this probability and maximize it, right? And solve for these equations. All right, good. All right, I have two more. Hopefully I have enough time to cover them both. Oof, going to be tight though. Okay. So the next one is segmentation by fitting a model. All right. And here, basically, the trivial idea, we'll talk more about more complex models in the second part of this course. But the simpler type of models that you can come up with are things like lines or circles or ellipsoids or conics, right? And things like that. And we know the equations of these things because we've drawn them 100 million times by now. And you just derive a method to find the points in the image, meaning the low-level image features I have extracted, right? So for example, the images could be the points of the edges on an edge detector, right? So I do canny edge detection, for example, and now I want to find those points on the edges that define a line or a curve or a circle or what have you, right? So the model here is going to be that mathematical equation. So for example, let's do detecting lines. So obviously, we know that the equation of a line is y equals mx plus b, right? We could use that equation. But the problem with that equation is that m and b are unbounded, right? I don't have bounds for these two variables. And that's going to be tricky. So it is actually more convenient to define a line as in polar coordinates as x times the cosine of the angle. That angle would be so a line is going to have, right, a line is going to have an angle, right, between the axes, right, or some plane that we define, right, and itself. So that's how the polar angles, the polar description of the line goes. You define the angle between your line and the axis, say the x-axis in our case, right? And then plus y, the sine of the angle, plus r, where r is the radius of the circle that defines the position of that line, okay? And the advantage of this is that now this defines a space where I have in one axis the angle and in the other axis that radius of the parameter, and those two are bounded, okay? So we're going to assume, so for example, theta obviously is going to be larger or equal than 0 and smaller or equal than 2 pi. And r we're going to assume cannot be larger than some r, capital R, okay? Some fixed point that we determine. Okay, now, if I have a point, if in my image, this is my image, okay? And in my image, I just happen to have this one point here, right? How many lines cross in my image plane cross that one point? Infinite, very good, right? There are infinite number of lines, right? So this is one of them, this is another one, this is another one, this is another one, this is another one, and so on, right? All the lines that pass through that point, right? There's an infinite number of lines that cross that point. And all these lines that cross that point are going to be defined here as this equation, which is a curve, right? This cosine plus sine, it will look something like this, right? And now each position on that curve defines one of these infinite many lines, right? So if I have, you see how this works? If I have the value here, this value, theta O and RO, that defines, this point here defines, I put the values here, and defines one of these lines, right? One of these infinitely many lines, true? Okay. Now if I have 2 points, say I have these 2 points, then there's going to be this line, right, that connects these 2 points, because 2 points are always a final line, true? But this point also has many other lines that do not cross that point, right? This other one, and so on, right? And these are going to be defined by another curve in my space. And in that space, there is going to be one location where these 2 curves cross. And what's that position? That position is the line that connects these 2 points, because these 2 points do have one line in common, just one. And that obviously is the one where these 2 curves cross, right? Perfect. Now, for 2 points, that has absolutely no interest, because 2 points always define a line. But what about if I have 10 points in my image? Now, 10 points are going to give me 10 curves in that space. And if they define a line, they're going to cross at one single location. But, there's always a but, right? But what are the chances that 10, 100, 1,000 points are perfectly aligned, defining a line and crossing in just one location in that polar coordinate space? Very small. So what we can do 2 things, right? We can use linear least squares to find a solution, right? Or you know what you could do? You could reduce the resolution of the image, the size of the image, and by doing that, you're actually eliminating that inconsistency of small differences between the different points in the line. Or another thing that you could do, instead of waiting for these to cross at a single point, look if they cross a region of that space, right? So all these solutions are acceptable. Another way to do that is to use ransack, remember ransack, to actually eliminate outliers, okay? And so on. But you can use all these different methods to find lines in your image. So if I extract edges from an image, or features, T unions, L unions, unions in general, scale-spatial unions, space-scale unions, or I can use any other type of local features that I have extracted using low-level vision. Now I can determine whether they align, right, according to the equation of a line, or maybe I'm interested in a circle, right? And I want to do this for a circle. And then I don't think I have this here. So if I want to do a circle, then my model is going to be x is equal to a plus r, the cosine of theta, y b plus r, the sine of theta, right? And now this is my new model, right? And that again defines now a circle in that space. Okay? And now the circles that intersect with one another gives me solutions, right? And so on and so forth. And this space here is called the half space. H-O-U-G-H, half space, okay? All right. One more method, and we're done. The last one is segmentation using deep convolutional networks. Okay. So we have already defined what a deep neural network is, right? A deep convolutional neural network means that some of those layers that we had in our network are going to be linear filters. That's it. That's all it means. Because these linear filters are defined by convolutions, right? Or correspond to convolutions, right? Convolving the image with a gabor or with whatever you want to select it, right? Okay. So we're going to use convolutions to compute low-level features from the image, and then use nonlinear least squares, gradient descent, to find a solution for image segmentation, right? Or semantic segmentation when we get to that as well. All right. So one typical, this is not the only solution. Again, there are many solutions out there. But let me briefly comment on one of these solutions. One solution that people have used, let's see, is to use, so for example, we can use what is called the Aton's convolution, which is given by y of I is equal to the sum of xi plus rk plus wk, where R is the sampling rate. K is the summing term here that I'm summing over. Y is my solution. X is my input. So this is, we call this the input or the observation, if you prefer. Input signal. In fact, let's say one-dimensional input signal. Why not? One-dimensional input signal. And Y is going to be my output, right? The output meaning the Aton's convolution, right? Okay. And as you see, this has the form of a linear filter that we have covered here in this class, and that we also we gave really extensive detailed description of this in 5460. And this is, of course, my filter, right? Or my kernel, if you prefer. OK. Now, the sampling rate, what that means is that when I do the convolution, so if I take, OK, let me do this in 1D, not in 2D, because in 2D it's very complicated to draw. But let's say this is my result of the convolution, and these are my input. OK? Now, if the sampling rate R is equal to 1, that means that I take the linear filter of these neighboring pixels, right? But if R is equal to 2, for example, right? So let me do this. How do I do this? So it looks something like this. Does this make sense? So this one takes these first 3, and the second one takes these next 3, and the next one would take the next 3, and so on, right? But with a sample rate of 2, what I do is I only sample every 2 of them, right? So I take this first one, then I would jump 1, 2, take this one, then 1, 2, take this one, right? And so on. And then here I would take, if I start with this one, and then I take this one, and then I take this one, right? You see how this works? And so on. What is that equivalent to that we have already covered in this class? Doing that sampling like this, what would this correspond to? To different what? Some different scales, right? Very good. Remember space scale theory? That's exactly what this does, right? It computes the convolutions, the linear filters, at different scales. So that corresponds to the low-level features that I'm actually extracting from the image, right? Different convolutions with my filter, with my kernel, at different scales. Correct. Very good. All right. So kernels that are typically used, this just for your information, I'm going to post a paper, obviously, of this in Canvas. But typical size for the kernels are 3 by 3, 5 by 5 are typical kernels. The rate tends to be like, I don't know, 2, 6, 12 values like this. And then with this, you create a space scale response of all these filters, right? So this is like the layers of your deep neural network that compute all these different convolutions. So you put all this together, and then you can formulate this as a graph. You have to represent this, all these layers as a graph as part of this deep neural network. And one way to do this is use conditional random fields. So we're going to define these convolutions with a conditional random field. Now, just very briefly, as a quick summary, this is going to be obviously given by a graph, right? With number of vertices and edges. And my observations x, remember, so x here are my observations, right? And with that, I'm going to define the conditional probability of y given x as the prior probability of y, okay? And then all the conditional probabilities of every observation I have given y, right? And now this is, I do the product of all of these from 1 to as many as I have, right? And that comes from base, right? Now, this is only one option I want to make clear. You could, don't write this down, please don't, but there are many other options. If you've taken my machine learning course, for example, you'll know about logistic regression, right? So you could actually use the logistic regression model here instead. You could use a variety of models, whichever model works best for you. And then in a conditional random field, a CRF, what you assume is that for the joint probability, the current computation y of t only depends on the prior observation or computation rather y at time t minus 1, right? Or at t minus 1 iteration or a scale or what have you, okay? So you can write, or the previous layer of a network. So you can write this as, this is the product from 1 to capital T of p y small t given y t minus 1 times p x t given y t, right? So you still need to define a metric to compute this. Typical metrics that are going to be used are the exponential function, as we did before with the graph-theoretic methods. And this will give you a set of equations that you can solve with nonlinear least squares, okay? And that is deep learning, okay? All right, just in time. This is it. That's all that's going to be covered in the midterm up to this point today, okay? So make sure to review all these things and look in Canvas. I'm going to post all these materials, all right? See you next week.